Hello guys, in today's video we are going to delve into the fascinating world of graph theory, particularly focusing on the depth-first search algorithm. We'll explore key concepts and mechanics behind it and see why it's a critical component in various applications. So let's jump right in. Before we deep dive into depth-first search, it's crucial to understand the fundamental data structure used in its implementation. A stack is a dynamic data structure that follows the last in, first out, or LIFO principle, as you can see right here. This means that the last element gets added to the stack and is the first one to be removed. So element 4 comes in, element 4 goes out first. A stack resembles an array in many ways, but differs primarily in how elements are accessed. With a stack, you can only access the top element, and this characteristic makes it immensely suitable for numerous applications in graph theory, the mathematical study that explores the relationships between objects. So as you can see, element 4 comes in, element 4 is last to leave, and after element 4 leaves, you can move element 3, then 2, then 1, but you can't access element 2 before element 3 leaves. So graph theory allows us to model networks of interconnected objects and study their properties and behavior. It provides the foundation for understanding the structural and quantitative aspects of complex systems, which can range from social networks to computer networks. Graph theory is used everywhere in the world. Now let's dive deeper into depth-first search, or DFS. DFS is a graph traversal method used to explore all the vertices of a graph in a depthward motion, thus named depth first. It has some key properties you should know. You pick a route and proceed along it. You continue until you reach a dead end or a previously visited node, and if you get stuck, you backtrack to the last node who has unvisited adjacent neighbors and then proceed down that. There are indeed multiple valid approaches to performing DFS, all aiming to explore the graph meticulously. You can choose, and all are valid ways. I will show you how to do it with always going to the rightmost element, but you could do it with always going to the lowest element, always going to the leftmost, and all are valid methods. So I will mark it green if it has already been visited, and I will mark it red once we know that there are no more options. So I'll start on 1, mark it green, and now that we're on 2 and we can either go to 11 or 3, we'll pick the rightmost element, so 3 in this case. Once 3 is visited, we check the rightmost element again, which is 4 this time. Visit 4, then we go to 5, and now we see once 5 is marked green, it has no unvisited adjacent neighbors. So we backtrack, and before we backtrack, we mark 5 as red because we know it has no unvisited adjacent neighbors. And then we go to 4. Next rightmost element that hasn't already been visited is 6. Then we go to 8, visit it, and then mark it as it has no unvisited adjacent neighbors. Same with 7, because we go backtrack to 6, then go to 7, mark it as visited, then mark it as red because it has no unvisited adjacent neighbors. Go back to 6, mark it as red because it has no unvisited adjacent neighbors. Same with 4, and then we backtrack all the way to 3. So then at 3, we go to the next element, 10, which hasn't been visited. Then we go to 9, and then 11, and finally 12, we mark as visited, and then no adjacent neighbors. Then we backtrack to 11, it has no neighbors. Backtrack to 9, has no neighbors. 10, no neighbors. 3, has no neighbors. 2, has no neighbors. And 1, finally, has no neighbors. And once all of the graph has been confirmed that it has no unvisited adjacent neighbors, we know that the graph has been fully explored. So now we will talk about how the stack that we covered previously with the last in, first out principle becomes crucial to doing depth-first search. So it helps keep track of the vertices and enables backtracking to the last node with unvisited neighbors efficiently. The systematic approach of diving deep through one branch before moving to the next is what makes DFS and using a stack in this manner uniquely useful. So now I will show you how a stack can be very useful when exploring a graph. So we visit 1, so we mark it green and add it to the stack. We visit 2, add it to the stack. Visit 3, visit 4, finally we visit 5, add it to the stack, but it's already has no unvisited neighbors that are adjacent. Then we mark it red, pop it from the stack. Go back to 4, it has an unvisited adjacent neighbor as 6, so then we add 6 to the stack. Go to 8, the rightmost element, mark it as visited, add it to the stack. It has no unvisited adjacent neighbors. Mark it as red and pop it from the stack. Then we backtrack to 6, move to 7 because it's the unvisited adjacent neighbor. Mark it as visited and add it to the stack. Has no neighbors, so then we pop it from the stack. Mark it as red. And here you can see how the stack is effective, because the path that will go back down is we follow 6 to 4 to 3. And you can see last in, first out. So 6, 4, 3, and the stack takes care of how the graph will be explored. So we'll mark this as red, and then we pop those from the stack. Now we're back at 3, and we go to 10, visit it, add it to the stack, and then go to 9, visit it, and add it to the stack. Go to 11 after that, visit it, and add it to the stack. And then we hit 12, which we visit and add to the stack. It has no unvisited adjacent neighbors, so we mark it as red and remove it from the stack. And then you could see the path that the graph will search to see if any other elements have unvisited adjacent neighbors. So we'll backtrack to 11, mark it as red, pop it from the stack, backtrack to 9, mark it as red, pop it from the stack, 10, mark it as red, pop it from the stack, 3, which we mark as red, and pop from the stack, 2, mark as red, pop from the stack, all the way back to 1, which we then mark as red. So then once the stack is completely empty, that's how we know we've explored all vertices in the graph. We're going to wrap up our discussion on depth first search here. I'll be coming out with some exciting leak code challenges that leverage this powerful algorithm. Depth first search can be implemented using recursion as well, besides the stack method we've discussed today. Let me know in the comments if you'd like to see how depth first search can be applied using recursion. Thank you so much for watching. If you found this video helpful, please hit the like button and subscribe for more content. And don't forget to hit the bell icon to get notifications on upcoming videos. Happy coding!